Hello everyone. In this video we will discuss improper integrals. So thus far we've seen mostly things that look like this, right? If we have a definite integral, it's from some finite number a to some finite number b, and what we get out is some number, right? We get the signed area. But a couple of things can go wrong or make this different. So, for instance, what if you see the integral from 1 to infinity of 1 over x, or the integral from 1 to infinity of like 1 over x squared, right? So in this case, we're talking about two things that look similar from 1 to infinity, right? We start here, but then we go on forever. And so what do we do with this infinite seeming area? Or at least it goes on infinitely to the right. Well, it turns out that this guy is a finite number, whereas this one is not. So somehow it has to do with how quickly this function goes to 0. So this is an example of an improper integral. And the thing that makes it improper is that it has an infinite bound. So if you saw negative infinity to something finite or to infinity, then you would also have an improper integral. So there's one other type, and we'll take another closer look at this later. So what if we have the integral from 0 to 1 of 1 over x, right? So this doesn't go to infinity with the bounds, but our function goes to infinity, right? Up here as we get really close to 0. So again, it looks like we have some infinite area to calculate. So how do we do that? So these are the two types of improper integrals that we will see. Those with a function going to infinity inside finite bounds, or a function with infinite bounds. All right, so now we will try to remedy this situation by saying how we actually deal with these things. So if we're going to infinity, then maybe we don't know how to deal with that, but we know how to deal with finite bounds, right? And so what we're going to do is take these finite bounds and then take the limit. Right, we've seen this process many times before. We estimate with finite things and then take a limit. So we're going to let this upper bound of our integral go to infinity, but it's going to be finite. I should probably toss a dx in there. And so this is how we'll define that. Okay, and so, here, for the integral to even have a chance to exist, and for our situation, we'll say that f of x is going to be continuous, for x bigger than or equal to a here. And then we will say that this integral converges. So call this integral I converges if the limit exists and is finite. So essentially, we've just turned this into a limit problem. And if we get a finite number out, then it converges and we're good. If it doesn't exist, or if it goes to infinity, then we say that I diverges otherwise. Okay? And this will be true for the other case as well in terms of the terminology, but how we will set it up is slightly different. So again, here we'll use the limit. So here we're going a to b, and so we're going to go a to the right from t to b. Or you can do it the other way as well, right, where maybe you have to play around with the upper bound. In this case, you would come at it from the left, and you would go from a to t, okay? So it's these limits that will allow us to approach these problems. All right, so let's start with this one. Let's do an example. So again, we're going to immediately appeal to this limit definition. So the issue is this upper bound, so we're going to take our integral instead from 0 to some finite t and let that t go to infinity. And then this is an easy function to integrate, right? So we're going to, again, keep our limit notation here. And then we get negative e to the negative x from 0 to t. So then what happens? So again, t is going to go to infinity, and then we just plug it in. So we're going to have negative e to the negative t minus negative e to the 0, aka plus 1. So really, it all boils down to this term here. So what happens as t goes to infinity? Well, it becomes 1 over e to a really big power, which is 0, right? So this is 0, this is 1, so this function's area goes to 1, even though it goes on infinitely to the right. So we would say that this converges. All right, so for your first exercise, I want you to try one similar. Go from 2 to infinity of 1 over x cubed dx. So as promised, I said we would look at this example a little more closely. So this issue, right, happens at 0, so we want to worry about that bound. We don't care so much about the 1. 1 is perfectly fine for 1 over x. So we're going to approach 0 from the left with this lower bound so that we're not trying to do 1 over 0 here. Then we still want to go to 1 over x dx. And so when we integrate, right, we're going to get the natural log. And you can kind of see here why this would be a potential issue, right? Because if I don't do the limit and I just plug in 0 to the natural log, well, 0 is not in its domain, right? So that seems like a problem. On the other hand, I can definitely take the limit. So this is a natural log of 1, aka 0, minus the limit as t approaches 0 from the right this whole time. I'm not stupid. So we're going to go from the right, and we will be taking the natural log of t, and we know what our graph of the natural log looks like, right? We're traveling this way as we approach 0 from the right, and that's going to be negative infinity. So it's like 0 minus a negative infinity. This guy's going off to infinity, so this diverges, right? We do not get a finite number here. So let's do one more example. So in this case, this should look a lot like arcsine, right, for our integrand. But first, our issue is what happens if we plug in 0. That's fine. But plugging in 1, right, that becomes a problem. We're dividing by 0. So that's the one we want to take care of. So we're going to go here from the left, of the same integral. So 0 to t now, dx over the square root of 1 minus x squared. Like I said, this is arcsine. So we have the limit of arcsine of x from 0 to t. So do we remember what happens with arcsine as t approaches 1? So arcsine of t approaches 1 from the left. So we're approaching the value 1. We need to find what radians gives us that. So that should be pi over 2, right? Sine of pi over 2 is going to be 1. And then minus arcsine of 0. Well, when is sine 0? At 0. So it's pi over 2 minus 0, or pi over 2. And this is another one, again, that converges. Okay? And so for your second exercise, I want you to take a look at the integral from 0 to 9 of 1 over root x dx. Thank you for watching.